Hello there and welcome back to this video series on control systems. Over the past few videos, we have been considering topics on frequency response, and in specific we have seen Nyquist criterion, we have seen minimum phase transfer functions, and then asymptotic Bode plot, and in specific we have seen for second order system, and then constructing asymptotic phase plot is considered, and we saw it's a good idea to calculate the exact phase and use approximation only when it is absolutely needed. This being the last topic that we are going to see on frequency response and Bode plots, I would encourage you to go through this very carefully. Watch videos 43, 49 and 54 to 57 before watching this video. Keep the notes handy to make the most out of this video. After watching this video, perhaps you will be able to infer the TF transfer function from asymptotic Bode magnitude plot. This is a beautiful feature essentially because you can take experimental data from which you can generate asymptotic Bode magnitude plot by approximate fit and fiddling with the data. From this Bode magnitude plot obtained from experiments, you can back compute what is the transfer function of the system, which may be used in further design process. So it's an important topic both from the practical utility as well as your examination. Though the procedure given here is very lengthy, it consists of basically 4 steps. 1. Identify the corner frequencies and identify the first order or second order terms. Then find out whether initial portion is an inclined line or not, and consider this lone S terms, that is S power 1 or S power 2 or so in the numerator and denominator. Then find the value of K. With this step 3, your transfer function calculation is done. Once the transfer function is available, draw approximate Bode plot and then plot it on your data to show whether everything is correct or not. You may also want to have the exact plot drawn to indicate the accuracy of the transfer function fit. So we'll just go over these 3 points one after the other. Identify corner frequencies. Corresponding to each corner frequency, you'll have a term. For example, at the corner frequency, if the slope changes by 20 dB per decade, that is just before, see what is the slope, just after the corner frequency, see what is the slope. If the slope changes by 20 dB per decade, you have a first order term. If it changes by 40 dB per decade, you have a second order term in the numerator. If the slope change is negative, corresponding terms are in the denominator. If the initial portion of the Bode plot goes up with a slope of 20 n dB per decade, an s to the power of n term is present in the numerator. If it is minus 20 n dB per decade, an s to the power of n term is present in the denominator. That is obvious, intuitive. If the magnitude goes up, there are terms present in the numerator. If the magnitude is going down, the terms are in the denominator. Then you will find the value of K. After finding all the polynomial terms, you find the value of K. If the initial portion of the plot is flat, find a constant value C where it is flat and use 20 log K is equal to C to find the gain K. If the initial slope is plus or minus 20 n dB per decade and it is no longer flat, you need to choose a value of omega 1 less than the lowest corner frequency. The word corner is missing. Less than the lowest corner frequency and read the corresponding M1. Obtain K by using this. Here you use plus sign if it is plus here, use minus sign if it is minus here. Now all the terms are evaluated. draw the approximate body plot over the data that is available and check whether all the calculations are correct. Also, you may want to plot the exact plot to show the accuracy of the transfer function fit. With that, we'll see a couple of examples. This is example 1. This plot corresponds to a minimum phase system whose body asymptotic magnitude plot. We coined a new acronym BAMP given below. This is a minus 20 dB per decade. This is again minus 20 dB per decade. You have 0 dB per decade. This is maybe this is an approximate plot, or this plot you obtained from experiments, and you are required to find the transfer function of such a system. Obviously, because the initial portion has a negative sloped line at minus 20 dB per decade, the value of n is 1. You can see here minus 20 dB per decade, and s to the power of n term is present in the denominator. So here n is 1 because it is minus 20 dB per decade, n is 1. You have an s term in the denominator. You have a corner frequency here and a corner frequency here. This corner frequency is 2 and the slope change is minus 20 dB per decade to 0 dB per decade. So there is a net increase in the slope. Similarly, the other corner frequency is 10. At this frequency again it fell down from 0 dB per decade to minus 20 dB per decade. Here, just before the corner frequency, the slope is minus 20. Just after it is 0, so the slope increased. So this term is present in the numerator. Here the slope fell down, so this term is in the denominator. This indicates a s term in the denominator. We'll note all these once again. Corner frequencies 2 and 10. Just before omega c1, the slope is minus 20, and just after, the slope is 0 dB per decade. So the slope increased. Therefore, 1 plus s over 2 is in the numerator. Similarly, 1 plus s over 10 is in the denominator. And because the slope is minus 20 n dB with n is equal to 1, and s to the power of n term is present in the denominator. So the transfer function is of the form k into 1 plus s by 2, s into 1 plus s over 10. To find the value of k, identify the smallest corner frequency. 2 radians per second is the smallest corner frequency. Take a frequency smaller than the smallest corner frequency. Let us say 1. Less than 2 is 1. From the plot, read gain at 1 radian per second. It is seen to be 12 dB. We'll just perhaps show it there. At 1, you can read the dB value. The dB value m you can find out from this equation, y2 minus y1. y2 is m, y1 is 6, m minus 6 divided by log 1 minus log 2. This line slope is minus 20. So you get m is equal to 12 and k is equal to 4. This is your transfer function. We will plot the exact graph on it, and you see it matches very closely. The maximum error is 3 dB here, 3 dB here. We'll look at another example of the transfer function of minimum phase system with body asymptotic magnitude plot BAMP given below. The initial portion is at 20 dB per decade. So you have an s to the power of 1 term in the numerator. Here the slope decreased. So 1 plus s by 2 is in the denominator. Here the slope is again decreased from 0 to minus 20. So 1 plus s by 10 is in the denominator. Here the slope again is decreased at 30. from minus 20 to minus 40. So the term 1 plus s by 30 is in the denominator. So the transfer function is of the form ks by 1 plus so on and so forth. So at 1 you read the value of 1. We chose this 1 because it has to be less than the lowest corner frequency. So this 1, it has 14. So at omega is equal to 1, m is equal to 14. Therefore you have 20 log k is equal to 14, which implies k is equal to 5. So 5s by all these terms indicate the transfer function. Just to be sure, we will calculate the frequency response and show on it, and you can see that it very nicely fits, except for 3 dB here, 3 dB here, and maybe a couple of dB here. The fit is amazingly accurate. So in summary, it is easy to back compute the transfer function from perhaps experimental data, and this also gives us an intuitive idea as to how to adjust the compensator to achieve a required transfer function. And the process of drawing Bode asymptotic magnitude plot, BAM, is really amazingly accurate. And I think that's all we have for now. Have a great day.